We're back. Streaming mathematics. It's another session. Just keeps on going. Okay. Let's see. Cool. Live chat. Before I jump into this, there is something like cool going down. On let me share this real quick. Oh, what's up, Johnny? I saw you already logged in today. Well, it's happening again. Looking at like dependency maps of like the US market and stuff is really fascinating. 11 companies that own everything, and the stake in those companies held by BlackRock. And these, geez. Kellogg's. Outrageous. Circular AI deals. Four main types of capitalism are oligarchic, state-funded, big firm, and entrepreneurial. When the big firms are owned by oligarchs, and if those firms run everything, they themselves become oligarchs in a way. And those big rich firms buy and fund seats into government. Eventually a new technology comes out like social media, artificial intelligence, and the entrepreneurs get to play with the big boys. They just get added into the recursive sequence of capitalism. Wow, that's a great way of looking at things. It is self-referential sometimes. Money isn't the trade, just debt trespasses. And someone, if they don't somehow declare bankruptcy. Fun game to play is Google the most recent big companies that declared bankruptcy and see if they had terrible business model or they are evil. Like trying to get out of paying lawsuits, restitution, and stuff. Recently, Vanderbilt Holding Company / Vanderbilt Minerals declared bankruptcy after it was found the talc they mined also contained asbestos, which eventually killed a bunch of people. Wow. I was wondering, new Macs came out for, what do you think is actually worth it? Did new Macs come out? Also, this is cool, like dependency graph of all the different dependency graph. Oh wow, dependency graph. Yeah, I didn't know that was a feature. That's awesome on GitHub. Did new Macs come out? MacBook Neo. What? That's pretty good for a MacBook computer. Apple's usually in the $1,000 range. That's not bad at all. What kind of What kind of specs does it have? Blah, 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 normie shit, blah, blah, blah. Where are the specs? Okay. A18. A18? What's A18? How many like gigs of RAM does it have? 8 gigs. That's weird. An M5? What's the M5 like? I don't know. My Mac is pretty good. That's a Chromebook replacement. It's an iPad with a keyboard. The iPhone chip. Alright, enough tech nonsense. I'm really here to do mathematics. And let's switch to saying there's a, I don't know, there is, fuck, a problem earlier that I was like confused about. What was that, though? I guess it's proving... Yeah, this algebra was kind of not the easiest thing in the world for me. Like, so I know this is the distance from the edge. But getting that algebra worked out. Yeah. If epsilon is less than that, or maybe we want epsilon greater than that, actually. Epsilon greater than that. So epsilon, that would kind of imply like 1 minus squared x squared plus y squared is less than x squared plus y squared. And I don't want to confuse, so I could call this A and B because that's technically different. But yeah, I don't know. It's not the clearest thing in the world. The epsilon should work. Yeah, I spent a while figuring out the epsilon, but like, why does the algebra end up working? I don't know. You can, of course, always choose a smaller one. Like, what about that as a smaller one? Would that make things easier? Because then we could get like a minus x squared. Can you do that? Like, I'm not even sure what the end goal is there. Johnny, if you're willing to hop on a call, I'd love that. Midterm is tomorrow. Give me 5 minutes. I'm just kidding. Cool. So, prove hold on. What? Reason for the buttoned up shirt? Dude, it's I don't know. I'm feeling fancy. Don't gotta be a reason for everything. Man, dude, that's annoying. Like, I just got fined $50 because I didn't like put enough money in my account that my rent is drawn from. Like, I have the money, it's just like in a different account. Fuck. Okay, I can deal with that later off stream. It's a fucking boring thing to do on stream. I think I have a solution to show openness without continuous maps by showing an open ball centered at any point exists. European appropriate attire for crowdsourcing math. Drink more water, 888. Boltzmann Ghost. I'm just trying to figure out, like, again, how I effectively do the algebra for proving the unit ball is open with the epsilon definition. Whoa. Like, apparent. So this distance function works, but could I also pick? Something's not updating about this preview. I wonder if I could also pick like this without the square root. Well, we need those parentheses still. And then, like, say All right, I'm calling up Johnny real quick. Yeah. Big Pepe, you should add me on. Well, send me an email. I'll add you on Discord or something. I'll put you in the server so it's easier to get a private types document.
What's up, man?
Hey, how's it going?
I'm good, man. How are you?
Pretty good.
Good. Very nice. Yeah, I saw you logged in earlier today already for a stream.
Yeah.
Yes, sir.
I gotta get a good grade on this analysis class.
I mean, yeah. Do you have a lot of midterms for this class, or is it like this one, like a lot of points?
No, I think we have 2 midterms in total. Yeah.
Okay. I mean, still, I guess two midterms and the final exam.
Yeah.
Oh damn. I guess that's quite a lot. But I mean, I think it's a good thing. I don't know. I've always had it where you have like very little in between. So most of the time you just had one big final exam at the end, and then like homework in between. But it's kind of stressful if you ask me, because like a lot depends on that final exam.
Yeah, I get that. Oh, why am I the types to give this to Big Pepe? Yeah, I think I'm honestly not someone who really stresses about school very easily for some reason too. So either structure doesn't bother me. Yeah.
I think that's very useful in general.
Oh, somebody. Okay, I don't know if you're watching the stream, but yeah, I was just like, I keep getting stuck in the algebra of doing like the epsilon computations.
For this problem, like with the open unit disk, showing that it's open.
Yeah.
Yeah, I think this one is a good old triangle inequality. I think I can simply show you, or I can share my screen again. It's like easier to communicate maybe.
Okay, cool. Yeah. Yeah.
Going on. Okay, now I see. So let's see. We want to show that the unit disk is open. Just from the definition, we can do this. So, what's like the setup? We're given give the unit disk a name. Let's call it D.
Yeah.
Given x, y in D. We want to find some epsilon ball. We want to find some epsilon ball around x and y,
right,
such that it's still contained in the unit disk. So, I mean, given that x and y in the disk, we know that we have this inequality, right? That's just given, and so we want to choose some epsilon, and you already very wisely chose. If we just choose epsilon to be this thing, which is something, this is strictly bigger than 0 by our assumption, so this makes sense. So this is the choice we make, and then we want to show that this everything that's within an epsilon distance of our point x, y, is actually contained in the unit ball. Do you have like a visual idea of why this should be the case?
Yeah, I have a very good visual idea of it. It's just like the algebra,
okay.
the triangle inequality.
Yeah, fair enough. No, but if you have the visual idea, that's the most important. Then it's very good. So let's write down what do we actually want to show. So we're or like let's say suppose we have some other points, I think like a comma b in, what was your notation, like v stop epsilon of x comma y. So I'm just meaning like no more than epsilon distance away from x comma y.
Sure.
Then we want to show that that it actually lies in the unit disk, right? That's our goal.
Right.
So so our goal, to make it very clear, is to show that our goal is to show that like that this thing is less than 1, and we are given that so a comma b lies an epsilon distance away from x comma y. So literally translating just means that if we consider wait, I should write this down carefully though. That like a minus x all squared plus b minus y all squared. I guess we don't need the absolute value, that this is less than epsilon, which is just 1 minus the square root of x squared.
Wait, can you explain how that term on the left is derived?
I think this is just like almost by definition, like what does it mean, like distance from a comma b to x comma y.
I see. Yeah. Gotcha.
Exactly. Yeah. Maybe. And now we want. So we have a goal, and like what this up here is saying is that just the distance of, let's say, a comma b to 0, 0, right? That this is less than 1. That's all we want to show. Phrase that way.
True. Yeah.
So, I guess, maybe let's do this in terms of like distance functions. I think it will make a bit clearer of like how this triangle probably works.
Okay.
So like our epsilon is not x, the distance from the 1 minus distance from x comma y to 0, 0. That's how we chose our epsilon. So now we have our goal and a given is put in terms of distance functions. Now, if we just consider the distance from a comma b to 0, 0, this is what we want to estimate in the end.
Yeah.
By the triangle inequality, this is less than or equal to the distance from a to b to x comma y plus the distance from x comma y to 0, 0.
Right.
This is what the triangle says, right? It's like if I have 2 points, in this case a comma b and 0, 0, like the straight line distance from them is always the shorter. So if I first take the distance to a third point, x comma y, and then go to my second point, like I'm taking like a roundabout way, the distance of like taking that in between steps.
Yeah. That makes
That's kind of
sense.
what's going on, right?
Yeah.
And now by our assumption, our assumption literally just tells us that this thing is less than 1. So because what is our assumption? Let me just, right? We have kind of this, just connecting the things. So if I move the distance from x to y to 0, 0 to the other side, if I add that on both sides, I get exactly what we need.
Yeah.
So does that make sense?
It does make sense. Yeah. I guess the triangle inequality, like, with distance functions, it makes a ton more sense.
Yeah, exactly. That's always like, yeah, and then you can translate this back into square roots, but it's like kind of, it doesn't really add anything to the problem, right?
Yeah.
It's just something purely because we have an inequality satisfied by these distance functions called the triangle inequality. So one thing to note, for example, is that this proof will work for any kind of distance function which satisfies the triangle inequality.
Right.
So this will kind of work in any metric space. And this is a proof that a unit ball or any ball of any radius is always open in any metric space.
Yeah. I see.
Which is very cool.
Yeah.
But then, yeah, you can just translate back everything into square roots, and then you just have to, like, this inequality in pink, which we got from just these are distances, you say, because triangle inequality in terms of some algebraic facts, this will translate to. It's going to be something ugly, but it works.
Yes. And then what's the actual... We could make a substitution. I see how this is going to work. Yeah, we can substitute the distance from A to B and x to y with 1 minus x to y and 0, 0, and those two things will cancel, and then we'll just get our distance from A to B, and 0, 0 is less than 1.
Yeah, so exactly. So this blue inequality that's like our given is just literally translate to this blue inequality in the proof.
Right. Yeah. Yeah, that's genius.
Yeah, that's why it helps, right, with writing this in terms, or thinking about it like geometrically and having this clear picture. Like, yeah, this is just how I came up with it on the spot. Like, I didn't think about no square root. I'm like, okay, we have some kind of distance, and a distance function should satisfy like an intuitive triangle inequality where it's like going to a third point is further away. Like, that's all it is. And then that it's really about square roots is kind of like secondary. Not all that important anymore.
Yeah. Yeah. Okay, that is very helpful. I'm gonna see if I can actually write this out now with that understanding.
The whole on the screen.
Let's see.
It was in R2, right? That the question. Yeah.
Yeah.
I didn't. Okay, that's good.
Open unit disk.
Yeah. Trying to do this from scratch without realizing like, there's actually like a distance function triangle inequality going on would probably be, I think, rather cumbersome to get the inequality in pink where like the equivalent of the triangle.
Yeah, totally. Like, that's, I don't think, super easy to stumble upon, but yeah, it's very helpful to think about these as distance functions.
Yeah.
So if epsilon is greater than 1 minus the distance between xy and 0, 0, and we have that the distance between
I don't think you want the epsilon to be greater than anything. You want to choose it, or maybe less than something, but you can choose it equal to this 1 minus whatever.
Gotcha. Yeah. And for an arbitrary AB, we have... What's our assumption? Just that any element squared is less than 1? Or no, we're trying to show...
I mean, we're given, it's like suppose we're given some arbitrary thing, which is an epsilon distance away from x comma y, and that we call this pair a comma b. And then we want to show, that's our goal, that it's contained in the unit ball centered at 0, 0, so that it's distant to 0, 0, less than 1.
Yes, so we're showing that the distance of this AB plus the distance of, well, the AB to an XY is less than...
I mean, that's all we're given, that this distance from AB to XY is like less than this epsilon, because this is what it means to lie in the epsilon ball around x comma y.
Yeah. We're given that the so the proof is basically just breaking this into the triangle inequality.
Yeah. Being very careful about like what's given, like what's the goal, what do we need to prove, and phrasing these terms purely in terms of distances, and kind of almost becomes forced to just use the triangle.
Is 1 minus, so distance is 1 minus xy to 0, 0. And then using the triangle inequality, we can say from A to B is from AB to XY is the same as from 0 to AB. No.
In your proof, you don't have to write down like exactly what your goal is. I think just the proof will make it clear. So you start with the distance from AB to 0, 0, and you just simply make note of this pink inequality by the triangle inequality. This is true, and then by our assumption, we get this blue inequality, and then you're basically already done, because that's all you that was needed to show.
Yes. Yeah. less than abxy plus xy to 0, 0. abxy. Yeah, okay. I mean, I think my intuition with this is like just getting confused by like which of the points, like is it AB or XY that's like the intermediary point in the triangle inequality?
Yeah, I guess it's I mean the XY is kind of what we're using, so we try to like make a picture or something. I'll have to draw a circle on a tablet, like this is like the unit ball. So this is like B1, 0, 0. And then we're given some point, like we start with some point x, y, and then we consider like this distance. This is what we call epsilon, right?
Yes.
It's like how far is xy away from the far, and then we consider an epsilon ball around xy. Oh, this is up. No. Let me repeat all of that. This is supposed to be like a ball, right? But the thing is, like, it's totally just like the epsilon x, y.
Yeah.
And now we're choosing. I mean, from the picture, it's already kind of clear, right? That the smaller ball is contained in the bigger ball. That's
right.
Literally all we're saying. But like, how should we do this? Technically, it's like, suppose we take some. Let's put it over here. Suppose we take some arbitrary point A, B in the smaller ball, and then we have to show that it's contained in the bigger ball.
Ah, yes.
So that's kind of what's going on. So we have this point over here.
Yeah.
We have some point over here, and then what we want to do is we want to do like this. We want to consider this distance in
Right.
pink. That's what we want to estimate, but because we want to show it in the bigger ball, it's nothing but giving a bound on this distance. And how do we give a bound on this distance? We go through the dark blue path. So we consider this distance, and we consider this distance.
Yes.
So like that's why xy is kind of our intermediary point.
Right. And that bigger blue distance, yeah, that's bigger than the hypotenuse, or equal to it, I guess, if it's on the same line.
So we add up so this is the pink, and these two are dark blue.
Nice color coding.
And then we can call it in the proof, like this is pink, and these two are dark blue.
And
right? That's how we use the triangle.
You're just kind of starting with the triangle inequality, and from that you're just building to the given. Or to the goal.
Yeah,
sorry.
And that's so the first, to the goal, exactly. And then, I mean, yeah, I know what I have to start with. Like, I know, like, from my goal, I have to give just that the distance from AB to 0, 0 is less than 1. So, like, in the end, like, maybe in between that, but in the end, my proof should somehow start with this distance of AB to 0, 0, and it should end with a 1. That's like what I keep in mind. So I just start with this AB to 0, 0, and then I try to think of this picture. I literally just have this picture in the mind and say like, okay, I want to give a bound on this pink distance, this like diagonal one.
Yeah.
So I first, what do I know? Like I literally only have 3 points, and like I am given something with a third point. So I just, literally look at what I'm given. and just think of this picture kind of at the same time.
Right. And yeah, the algebra is actually quite simple. It's just like basically a single substitution.
Yeah, but it's kind of, you have to first make this like abstraction step with like, oh, this is just about distance functions, like these square roots and squares are completely irrelevant.
Right. Yeah.
So I guess that's like one step that has to be implicit. Otherwise, it will probably not look very nice.
Yeah. I think I get exactly what's going on now. Well, distance from xy to... Well, let me think about this instead of just looking. The distance from xy to AB, we know the distance of xy is less than 1. And
the way you've written it down, yeah, something is not. I mean, you have this first line with like line 133. That's
yeah.
I mean, I can't see the whole one, but that looks right. And then to go one step further, you just substitute what you're given for the distance from AB to XY, and you pick up this strict inequality. It's kind of important here that it's strict, right? Because
right.
Yeah, it matters for it.
And we have 0, 0. I guess I was substituting the wrong thing. And then y is going to be 1 minus the distance from... Oh, okay, yeah, I see what I was doing wrong. Plus... And then finally that will cancel out, and we'll just get 1. I don't think my preview is working or something, but... What problem is this? 12.
Like line 133.
Yeah. Yeah, okay, that helps a lot, actually, seeing that visualized with the triangle inequality and distance.
Yeah, that's nice, right? And I guess kind of from a meta perspective, because it's like something so basic, or, well, I guess for me it's like having a little bit of like being able to think one step higher and just thinking like, oh, this should be true in any metric space. Like, this should absolutely not depend, on the metric or the space around it. It's kind of like, yeah, there should be like a really easy proof which does not depend on doing any algebra at all, because it should work for any metric that you choose.
Right. Yeah. Yeah.
So it kind of helps, like thinking how should I do it.
Is that kind of like that seems like a recurring theme now that I'm getting into slightly harder math? Like, there's always another level of generalness that, like, you have like a more powerful, more general level on top of this.
Sometimes it fails, I mean, there's always some kind of abstraction about it. But sometimes, like, your theorem it's really like you have to somehow know, is my theorem that I'm trying to prove something that should be also true in this more abstract framework, or does it really depend on the specific situation we're considering here? You know, like for example, like a good example is this this Heine-Borel theorem, which says like compact if and only if bounded plus closed, right?
Yeah.
That's, I mean, like this is not something that's like immediately obvious, but that's something where, like, which is very specific about Euclidean space and its Euclidean topology on it, like this metric. This is like, it very much depends on that, and so this is not true in a more general case, like only in these Euclidean spaces. But yeah, this is something like it's hard to know beforehand, right? Like, should my theorem be true more general or not? Kind of comes with experience and knowing like the subject you're dealing with, and like knowing what to expect, kind of.
Right. Yeah. And also, like, wasn't real analysis kind of built before topology was?
Sorry, what is it before topology?
Didn't they kind of come up with like the formalization for those definitions in a real analysis sense before it was like formalized in a topological sense? Like the Heine-Borel is maybe older.
Yeah, it should be. I'm pretty sure it should be. Let's see. Yeah, no, analysis, I mean, was studied way before topology because people cared about like doing this limit stuff properly. So it's probably the beginning of the 1800s, somewhere in the 1800s, and then but people started, I guess, noticing, like people started doing like this analysis also like in multiple variables, right? Where you talking about distances of like sequences in the plane or something like this, and you kind of like, they started noticing these commonalities where like yeah, actually this proof doesn't depend at all that we're using like square roots and squares and all this stuff. It's just it has some very like concrete geometric meaning. So like what we're trying to do with a metric space, like formalize this very concrete like geometric picture, like what's the triangle inequality. But then so I guess there you get metric spaces, and then topology is kind of even after that, because it's like quite more abstract. It's like this realization that like distances are not really all that necessary. Like all you should care about are opens and closed, and a lot of things we can do, like compactness, we can do purely in terms of like open and closed steps.
Yeah.
Which this idea kind of comes from, and this kind of naturally leads to, or once you have that, you can do like analysis on things like, I don't know if you ever hold like a manifold. I don't know if this says anything to you.
Yeah, the weird graphy looking.
So like or for example, if you think of like a sphere, like this sphere is, in some sense, if you look at a small patch of it, it kind of looks like a plane.
Yeah.
But like as a whole thing, it's not the same as a plane. It's like qualitatively different. But so this is like kind of what a manifold is. It's like you have like open sets which cover the whole thing. Like around every point you have like a small epsilon neighborhood, or like an open.
Yeah.
To where it's the same Euclidean space topologically. But globally the structure makes it work.
Yeah. That is weird.
So, yeah. I mean, but this is the kind of stuff like people study. I don't care that much, I guess. But this like, so people do like, I guess I would say like one way of generalizing analysis is just like, changing the ambient space upon which you do the analysis. So we're doing it on the real line or the plane. But you can do it like on these kinds of manifolds. And then what you're doing is called differential geometry. So you can do like calculus and integrals and other stuff on these kinds of things.
That's sick.
I'm not all good. Yeah.
Yeah.
But there's some like crazy like terms, like you have the fundamental theorem of calculus, where it's like if you take the integral of the derivative of some function, then you just evaluate the functions at the two endpoints of the interval
Yeah.
over which you're integrating. This is kind of like what this really is saying. Okay, so you have this operator, like taking a function to its derivative.
Yep.
And once you take the integral, you just have some topological thing, namely this interval from A to B, let's say.
Yeah.
So you do the inverse of your derivative operator to get the original function, and you just evaluate it at the boundary, like this topological boundary of your interval. That's kind of what's going on. So if you look at like higher dimensional analogs, it's always the same thing going on. Like I have some notion of derivative, like maybe it's the curl or grad or diff or like any of these funny looking things.
Yeah.
And if I want to know the integral of the div of something over some region, then I take the boundary of this region and look at the integral of the original thing. Right. And this is like really nicely generalized in something called the generalized Stokes theorem, where this works on any manifold. And like this whole derivative thing is like all abstracted away.
Wow.
Very cool.
Wow. Yeah. Math is really cool.
Yeah. It's like, yeah. So some things can really be generalized into absolute oblivion. It's really crazy.
Yeah. I guess problem 14 has not been. I'm just doing like all the problems related to openness definitions.
Yeah, 14 is important. 14 is very nice. Because this motivates the definition in like for topological space. Because there you just say, I have a space plus some open, like this abstract notion of open set, but they should satisfy like that any intersection of opens is open, and any union of opens is open.
Yeah.
So that's very nice.
Okay, prove that. And give an example showing that an infinite intersection of open sets need not be open.
Yeah, only finite intersection of open sets. But yeah, can you come up like, let's see, can you easily come up with like an easy example in C? Like even on the real numbers?
Infinite intersection of open sets need not be open.
Well, for example, when just like with open interval. Okay.
Just with open intervals.
Yeah, you can find a relatively. I mean, we can also come back to it, but you can just do it like you can find a kind of example, for example, on the real line and just using open intervals. Nothing fancy.
Yeah, so I'm trying to think like need not be open. I was like trying to think of it as the closed definition, but obviously closed and open aren't exactly opposite, so
that's very true. Although in this particular case, or at least the example I'm thinking of, the intersection will by accident actually be closed.
I mean, infinite intersection of open sets need not be open. Well, I mean, like, if we could get an intersection that results in like a singleton set, that would be.
Yeah, for example, that sounds like a really good idea. Yeah.
That would be closed. And how could we get an infinite intersection?
Also,
of
don't look at chat. People are spoiling.
Okay. um, infinite intersection of open sets. So we could get a bunch of. I'm trying to think about this geometrically. Like, how can they all have one point in common but not overlap otherwise? I mean,
Yeah.
like,
So geometrically, yeah. But you're really gonna need like infinitely many. As soon as you only use finitely many, it's gonna fail because like any finite intersection of open is gonna be open. So you somehow really have to like abuse this fact that you have infinitely many to work with.
I mean, this is really like feels very janky, but like if you have like I don't know, say like one like this is your set. This is like one of there's gonna be infinite of these. Like a singleton union with like I don't know, like 2 to n and like where n is like n in the natural numbers and this is your set.
But like you want like an infinite family of sets, right? That you're gonna take the intersection. So okay, I guess I see what you mean. Okay, yeah. But is each one of those
Oh no. That would not work necessarily because there's going to be a ton of overlap here.
yeah, like so I mean first of all, each of the sets doesn't need to be open because it's like a union, a point union and interval. So there's like no epsilon neighborhood around that singleton.
Oh, you're right.
But
You're
also
right. Yeah.
the intersection is going to be like also just like the smallest one. It's going to be one union and then I guess two, some small interval.
Yeah.
I guess technically it also doesn't make sense to take the interval 2, 1, or it's not immediately like obvious.
Yeah. Okay. Infinite intersection of open sets.
But like one thing that I really liked about this example, well, it wasn't really an example, but about what you were trying to do was that like having the intervals nested inside of each other, like with this 2, n. But now what you kind of had going that as you had more and more open sets, like this interval that you considered got bigger and bigger and bigger.
Oh, I
like,
see. Yeah,
right.
yeah. It gets smaller and smaller. Yeah. That's a good idea. If you have like, I don't know, like 1 and then 1 over n. Well, I guess it should be like 1 over n to 1 or something. And
yeah, I'm just waiting still.
Would you eventually get... Oh, let's put like a big intersection around this. Big.
But here it's kind of, you're almost there, but I think the way you've written it now, like as n grows bigger, this interval grows bigger. So you start with like a half, 1, and then you have like a third, 1, fourth, 1. So this interval kind of keeps growing. But so if you take the intersection of like growing things, it's literally just equal to the smallest one. So the intersection of all of those will be just the open interval 1/2, 1. so that's still open.
But if...
Yeah. That looks really nice.
Yeah, assuming n is greater than 1.
Yeah, well, n greater or equal to
2, right?
1,
yeah.
But this is already very much towards the right direction. But can you think about what should the intersection of the thing be?
Yeah, I mean, it will be... I guess as...
I see Leo lectures in the chat. He's from K-Series stream. I know him. He doesn't know me, but I know him. So hello.
Yeah, he has his own channel too. I think what this would give you eventually is just the 0.1 maybe. Well, I guess it's never gonna hit 1, but you'd get closer and closer to the interval would eventually become very close to 1 to 1.
Yeah. So, what can you think of any elements which lie in this intersection? What kind of elements would lie in there?
I guess 0. 0.9. I mean, well...
but what if I take n to be bigger or equal to 10? Right? So then you're going to look at the intervals from 0 to 9, 1, but 0, 9 is not in there anymore.
Yeah, I see. Yeah.
0.9 is not in there. Can you think of some other thing which is in there?
I mean, n minus 1 over n.
You have to choose your point independently from n, right? Because it needs to be in the intersection, so it needs to lie in all of those sets you've written down.
Yeah.
Sketch. I mean, so what I'm trying to get you towards is that this intersection will actually be empty and therefore open.
Oh, yeah, I see. I guess I was trying to find a point that's, I don't know, it seems like 1, but it's obviously it can't include 1, so I guess there is nothing.
Exactly. It's you have this interval or this family of intervals where open, where the right side is fixed and the left side gets closer and closer and closer and closer to the right side, right?
Yeah.
So, and because they're both always open intervals, you can never find something which is in all of them, because always after some point the interval will exclude it if your n is big enough. So this is open. It's empty. This intersection therefore is still open. The empty set is open. So this is still not a counter or an example, but we're very, very close now.
Yeah. Yeah, so we need something that just narrows into a singular element, because...
Exactly.
Yes, but how do we do that with, it would be easy if we could just say, that one of these endpoints is, included, but that wouldn't be open.
Exactly. So, now we kind of, right, we have this one endpoint fixed, and we let this other endpoint of these intervals kind of approach it, to narrow it down and have this nested. But what if we, move both endpoints of the interval?
move them to, I mean, we could take 1 away from both of them.
So like the right endpoint we kept fixed, but what if we also let that vary with n?
Oh, that's interesting. Yeah. And how is that going to work, though? If we add 1 over n, then 1 will be in here?
I'm just waiting for the stream to update, but what you said, yeah, what you've written down now, that looks really good, right? Because like let's think about it like before.
Yeah.
Like this from both sides, it kind of approaches 1. So we're kind of looking like what happens to a really big n, because it gets smaller and smaller. If we have some number which is not equal to 1, like it doesn't matter if it lies on the left or the right. Eventually, its n's become big enough to exclude it. So any number, and then you can think about it again as lying some epsilon distance away from 1.
Yeah.
There will always be some n, basically because those sequences in the left and right endpoint, they converge to 1.
Yeah.
There's always like, if you take n big enough, then there lies some like epsilon distance close. So you always exclude those points. But the term like 1 itself, that's always in there by construction. So yeah, it literally is just the singleton 1, which is exactly what we want.
Yeah, that's like exactly like an epsilon ball too. That's really cool.
Yeah, exactly.
And okay, yeah, that's an excellent one.
Yeah, it's very nice to have these examples kind of like on standby to think of these things.
Yeah. All right. So what if you've got 2 open sets, and
Yes.
their intersection is open? Well, let's see. That means yeah, I like the way I would think of doing that, I guess. Just to talk through it before I write it out is like if U1 and U2 are open sets, then any element in either of those, like say x1 and x2, has an epsilon ball fully contained in U1 or U2. And then if you intersection them together, it's just like, well, the elements of U1 all are going to have epsilon balls in U1, and the elements of U2 are all going to have their corresponding elements in there too.
Yeah,
Like,
that sounds like the right direction in any case. But you only consider one element, right? You don't need to consider an x1 or an x2. You just consider some arbitrary element in the intersection.
Yeah.
And then you have some epsilon ball for which it is contained in U1, and you have some other epsilon ball for which it's contained in U2, because they're both open. And from that, you have to build a new epsilon ball to make sure it's contained in the intersection.
Right. So consider U in the intersection of the two balls. We have epsilon neighborhood of U in U1 and an epsilon neighborhood of U in U2 could you take like the smaller epsilon neighborhood to be your new value?
Yeah, that sounds about right.
Yeah.
I guess, yeah, you should call them like, you shouldn't both call them epsilon. Like there's some epsilon 1 and an epsilon 2.
Yes. And EN2.
Yeah, so you need to, I mean, yeah. Now you need to show that like that this new epsilon neighborhood is contained in both. But this is like almost by definition. Like, I mean, I guess you should write it out carefully.
Yeah.
There's like nothing really going on.
Yeah. Yeah, I mean, we lost Pepe.
Yeah. Leo lectures, I think, immediately dipped. Or maybe he was scared that anyway.
Yeah. Okay. And then seems like it would be a pretty similar argument for the union. Well, actually,
yeah, maybe.
or makes it a little bit different.
Yeah. I guess you should. I mean, maybe it's even easier, I think. Yeah. Yeah, it's gonna be even easier, I think.
So we have an epsilon neighborhood of 1. We have one epsilon neighborhood in U1 or, well,
yeah, so you just have to consider kind of two cases. Like once, what if U is contained in U1? Then I have this epsilon neighborhood in U1, but this will also be an epsilon neighborhood in union.
I see.
And then these exact same works for you too.
Right, that makes sense. Case U in U1, since U1 is open, there's an epsilon neighborhood of U within U1. Which is in U1 union U2. And then similarly, U and U2 implies epsilon neighborhood of U in U2 in U2 union U1. Yeah, that is very easy.
Yeah. But it, again, I guess the thing to notice here is that we only talked about epsilon neighborhoods and distances, or so this is purely again nothing about the real numbers whatsoever. This just says if you have a metric space, any metric space, then the union of two opens is open, and the intersection of two opens is open.
Yeah, yeah. Wow, I can't wait to take topology. That's gonna be cool.
Yeah, I mean, yeah, that's very nice. I think at sometimes like at the beginning when you're just doing really pointed topology, it can feel kind of like symbol pushing a little bit, but it's kind of because it's such an abstract like high level thing, it's like so applicable. So the basic things are just that abstract is just like working with these abstract open sets and this kind of thing.
Right.
But then once you can talk about manifolds or all this kind of stuff, it's like really cool. Especially like algebraic topology, where you kind of fuse topology with algebra. Oh, that goes so hard.
Yeah. Like, how do you must have like known at a certain point of doing math, like this is the area of math that I want to study.
Yeah, I guess. I mean, not as early as you might think.
Yeah.
Right. So I just like, for example, when I started my undergraduate, like just like a few months or weeks before, and I'd even decided that I wanted to do math. Like back then, I had zero clue. So I had no clue then. I just did my courses, and I mean, I guess I was just lucky, or maybe it was destined in some way that I had like an the introductory algebra course, like groups and rings and stuff.
Yeah.
Was like really well taught. It was like a very, very like this old professor was like a really good lecturer.
Yeah.
So naturally, I'm like, okay, I want to do more courses like this, and so I did some of the other algebra courses, and I just noticed that I liked those too, and so I just completed all the algebra courses, and I was like, damn, I have so much space left in my undergraduate, but no my algebra courses to finish. So I guess at this point I noticed that maybe in the masters I should do like a focus on algebra and related things.
Yeah. Yeah.
But yeah, I mean it kind of depends on the program. But for example, in my university, like officially, like the master's program is just like mathematics, and then within it you kind of have tracks like topology or more algebra or more applied stuff. But this is like not very like rigid or something. Like there's a lot of overlap, and you can do like a lot of courses from different areas, which is really nice, I think. So I can although I do like number theory and algebraic geometry and stuff like this, I still did like algebraic topology courses in my master's, which is like a really useful to do.
Right.
Because there is like connection between these fields, and just like at this point also to get like there's like a really like a strong not only like direct connection between the fields, but also like a flow of ideas both ways, like how things came to be, why things are a certain way, like where techniques come from. It's like a lot of overlap between these ideas, so it's really useful. Like even if you do algebraic geometry, to be like at least a bit well versed in the language of algebraic topology and stuff.
Right. Yeah. I think I'm really getting into it, honestly. Like seeing how math has all these dependencies and stuff. It's really cool.
Yeah, right. Yeah, it's the dependency tree goes like crazy. I tell you, it goes absolutely.
Yeah, I really like the I don't know, my professor will often like talk about kind of the history of math, and I find that really cool too. Like what people discovered what and like at what time.
Yeah, that's true. Like I don't know much about it at all, but like just from the things I've heard, it's always very cool. Like I mean, I might be ever so slightly biased, but you have this guy, right, who's well, not the founder, but like one of the most important people in algebraic geometry.
Yeah.
Like Alexander Grothendieck. You've probably seen like his name in the chat. Like he lived like, or he was like worked like from the 60s onwards. but he had like a super interesting life. It's like so cool to hear about. I think there's like there's like podcasts about it on YouTube. It's very cool stuff.
Yeah. I know what you mean. All right. I wrote down this question in the meantime. Problem 15.
This was pretty quick, right?
Yeah, it's considering. Oh, that's.
Okay. So you need to open no close.
Okay. Neither open nor closed, I think. Sometimes I just want to like break to a different page because like the page breaks are really annoying.
Yeah. Let's see. Why should this need to be open? Close. Okay, so I guess this one is kind of harder to visualize, right? It's like, how do you even visualize that set? It's like all the rational numbers between 0 and 1. Like,
yeah.
There's a lot of.
It's neither open nor closed. So.
Yeah. So I think the easiest is to start with that it's not open.
So, I mean. Oh, not open or not closed in R. I mean, yeah, I see intuitively why that's the case because, like, if you have, like, an arbitrary element, X in E, then, like, an epsilon neighborhood is going to intersect real numbers because there are, like, reals in between rationals.
Exactly. Exactly. That's the idea. Very good. So that shows that it's just not open. So do you want to try to like type that out for me? Yeah. I think it's so useful to have like a careful written down argument.
That's like, I don't know how I would say it, but maybe there's a more rigorous way to say it.
I mean, what you said is like perfect, like for the structure of a proof. I mean, you have to like when you write it down, you have to say a few things more, I guess, but that's basically it what you have. Because like, if it were open, right? You kind of argue by contradiction. Suppose it were open, then there would exist some epsilon neighborhood contained in E. And then you indeed argue like, right? If to say how to argue about it carefully. You have some X, it's rational. You have some epsilon neighborhood, and you have to say that every epsilon neighborhood contains some irrational number.
Right.
So, I mean, I think it's fine to just say that, like, any epsilon neighborhood will intersect the numbers which aren't rational. You can also prove this. I guess it's a bit annoying. So, I think this is fine. Especially on the exam, it should be fine.
Someone also mentioned, which I wanted to bring up really quick, is differential equations. Because also, I hated differential equations. Like, that doesn't feel the same as this math to me. It feels too applied.
Yeah, me too. I guess we all had to do it, but it wasn't like a pure math differential equation, but it was so boring. Couldn't. I mean, we proved like some things, like the existence and uniqueness of differential equations in certain like things, but like it was more indeed about solving them. It was, yeah. I didn't pay much attention to that course. I had like a fun algebra course to do at the same time, so I just put all my time into that.
Yeah, that's yeah.
But I mean, yeah, you have to see like I don't know what what your university offers, but in general, there's like always so much cool math out there. Like you could fill so many undergraduate programs with so much cool math. It's just you kind of have to see like what you can get your hands on.
I want to see what other things. What is this summer? I want to see what other classes are being offered right now, just as an idea for. I guess we have.
Yeah.
Algebraic geometry.
Oh, where? Let me see. Is it a undergraduate or a graduate class?
Well, it might be graduate actually, but you can take graduate classes in undergrad at my school.
I guess you can. Let me see.
Topology.
Okay, it doesn't have much info about their cover.
Master's thesis for each graph, forcing numbers, topics and combinatorics.
What is this like? IS, IS topology, IS algebraic geometry.
I actually don't know IS.
I see theory of functions of complex variables. That sounds like complex analysis. That complex analysis is very cool. It's like you have like real analysis where you have to do everything so carefully, and there's like lots of like counter examples you will see later in real analysis where like things are very awkward, but then you do complex analysis and it's like God created the earth, everything is good, like everything is exactly how it should work out. It's so nice. The complex numbers are much better than real numbers. It's crazy.
Huh. Yeah, you wouldn't think, but
yeah, no, also in algebraic geometry, like the real numbers, like it's so fucked. I see. Yeah, that's 2 semesters of real analysis required. Yeah, but it's like that's an introductory course into complex analysis. That's really nice. Calculus of residues. Oh, that goes so hard. Like it gives you like these really really neat tricks to calculate integrals.
oh,
For example, right? Like in real analysis, like real functions are like kind of whack. Like you can have a function which are like like differentiable once, but then once you take the derivative, like you don't know what happens. It could even be like not continuous, or like it doesn't have to be differentiable twice. But like if you have like a complex function on the complex plane, which is differentiable once as a complex function, then it's automatically differentiable infinitely number of times.
Oh wow.
Yeah.
Weird.
It's very cool. And you have like, and again, I guess thinking topologically, if you have like 2 like such functions you call analytic if they're like this complex differentiable, and then if you have 2 such functions and you have any like epsilon neighborhoods in a complex plane where they agree, then they automatically have to be the same everywhere. It's really really strong.
Yeah. Real quick, also Tim Duncan. I'm a fan of this guy because he said something funny once. He says, "How do you motivate to take these pure theoretical courses?" It would be interesting to hear your answer on that.
I mean, I guess the short answer was just it's what was fun for me in the moment. There was like no like, let's say, very deep reason. For me, it was just I don't see like it's not like I had to come up with a reason for myself,
Yeah.
Like it's like the other stuff is more applied, so I better have a good reason if I want to do this more pure stuff. To me, it was always like I just do this math thing like mainly. Yeah, I don't see it like as a, oh, I need. Oh wait, my headphones just died. Can you still hear me, or is it really fucked up?
It sounds better, actually.
Oh, that's crazy. Yeah, we love my headphones. So great. Um, so like to me, it was not like I did math like to like, oh, I need to do this to get a like good job or something, so I have to take like courses which jobs want. It was just I do this like because I'm very interested in it.
Yeah.
So I just follow this path, which is like most interesting to me, like the path of least resistance in some sense.
I think that's like, honestly, even the people that are, well, people that do things that are more career relevant, not to like totally roast you, but like if you're doing like I don't know, programming or software engineering, but you're doing it because you're interested in it rather than because you're interested in like what an employer would be interested in. Like if you're doing it for the love of the subject, it's just like way easier, I feel like.
Yeah, no, I believe that. I believe that. Yeah, I don't know. It was just for me, it's kind of like this math stuff is what like I just noticed I was interested in and that I really liked, so I can follow this. But I mean, yeah, definitely. If you like more like this career-oriented stuff or this stuff, if you like that, you should definitely do it. I mean, don't let me stop you.
Yeah. All right. So showing something is not closed, you could show that there's a limit point of it that it doesn't contain.
Yes, for example, yeah. Another way here would be to show that the complement is not open. But both
Yeah,
ways are fine, I think.
that seems nicer, honestly, because I can't think of off the top of my head like an easy way to.
Or, yeah. Or
Because,
even a third way, because it's certainly bounded, right? Because it
yeah,
lies within the interval 0, 1.
yeah.
We could show that it's non-compact by finding a cover which has no finite.
That's crazy.
I mean, it's a very valid way.
Yeah.
But I think we can do like multiple methods. It will all kind of like, yeah, it will be quite similar, I think, or it will all give you like, yeah, the same idea.
Yeah, that is a clever thing. But showing the complement,
So let's see, yeah, showing the complement is not open. So we just have to find literally any point, like, or it's enough to find one counterexample of some point where no epsilon neighborhood around it is contained in the complement.
I mean, what about like something irrational?
Uh-huh. But will any irrational do, or do we have to pick something specific irrational?
Yeah, we do have to pick a specific irrational that like is bordering on, because the complement of that is gonna be like, well, it's gonna be like negative infinity to 0.
I mean, there's gonna be
Right.
more in the complement, not just that, right? It's like everything outside the interval 0, 1 is in there, and then within that interval, it's like the irrationals.
Right. Well,
So
the
I
irrationals,
think
right?
yeah, all the irrationals between 0 and 1, right? So I mean, if you think about it, like if you pick something outside the interval, so for example, less than 0 or bigger than 1, that's not gonna work, right? There, I can actually find an epsilon neighborhood.
Yeah, you can. So you're gonna have to pick something like an irrational number inside the interval.
Exactly, exactly. So let's suppose like we have it. Like we can pick an explicit one, or we can just say, right, there exists one, let's call it x.
What about like 1 over root 2?
Yeah, that works.
1 over pi?
That also works. But like maybe your teacher asked you to show that pi is irrational, and that's not fun.
Yeah,
Like,
I'd prefer
1
to
over
show
root
root
two is
2. Yeah.
Let's see. So we have this number. So what do we want to show now? Well, I'll still just call it x. That any epsilon neighborhood contains something not in the complement, i.e., it contains something inside the set. So a rational number between 0 and 1.
Yeah, I mean, but how do we... That's not the most intuitive thing in the world to me.
I mean, in the end, it's again something like, suppose like it's somehow that the rational numbers are dense inside the real numbers. But what does it mean? It's just like you have this x, and you can find rational numbers arbitrarily close to x. Like within any epsilon ball that you choose around x, there's always some rational number going to be inside an epsilon ball.
Okay, cool. Could we just, for sake of like learning, like see how this would be proved using one of the other techniques, like showing that it's not compact?
Yes, yeah. We can very much do that. Let's start with making like showing that it's not a limit point, or I want to say like it has a limit point outside the set.
Showing that it has a limit point outside the set for the definition of compactness, or do you just want to
show that? No, for showing like the set is closed if it has all its limit points, right?
Gotcha. Yeah.
So we're gonna find the limit point, which is not inside the set itself, and this will tie back to what we're gonna need to do in part B of the exercise. So I guess it's really useful if we do this.
Okay.
So we want to find some sequence where every element of that sequence lies inside our set E. But we must have that this sequence converges to a real number, which does not lie inside the set E.
Right, and so we need a series of rationals converging to an irrational, essentially.
Exactly. Yes. Very good. That's exactly the point.
But
can you think of like maybe not in terms of formulae, but like maybe just I don't know how to say, it's more like a description of how you could construct something like this?
I mean, not especially, like, I guess.
Or maybe let me phrase it another way, because it's kind of like, let's say I fix some irrational between 0 and 1.
Sure.
Doesn't matter which one, but it's some irrational number x between 0 and 1. Can I always find a sequence of rationals which converges to that irrational?
No.
Why not?
Well, I mean, yeah, I don't really have a reason other than like it doesn't intuitively seem possible, but I guess.
Fair. But for example, like if I think of this irrational, it has like some decimal expansion, right? Like between 0 and 1, so it's like 0, comma, something that goes on forever.
Yeah.
Like if I consider a sequence where I just each term of this sequence is just this decimal expansion, but cut off after a certain number of digits. So the first term is maybe I cut it off after the first digit. The second term of the sequence, I cut it off after the second digit. Like,
right, and because
each
they're
of these
finite,
cut-off
they're
values-
rational.
Exactly. Because I cut them off, like at every point, this is rational, but it converges to this infinite decimal, which
Right.
by construction was irrational.
Yeah, I guess I get that, but it's like a little bit. It feels like it's too manual. You know what I mean? It's like for pi, it's like you're gonna go one by one and like choose a. It seems like there should be like some more automatic way to do it, like induction, I guess.
A constructive way that a computer could do. Very true.
Yeah.
I mean, welcome to the world of constructive mathematics. You're interesting, but yeah, I'm afraid maybe there is, but there's not a super nice way, because it's somehow like if you have some general irrational number, like, or maybe like from a computer like point of view, right?
Yeah.
There, like most irrationals are uncomputable. Like you can't find them in some sense with a computer. Do you know this, or does this?
Yeah.
Why this should be the case?
Right. You can't. I mean, you can approximate them out to large numbers, but
Yeah, but like even in some more abstract sense, like there are uncountably infinite irrationals between 0 and 1,
yeah.
right? But there are only countably many Turing machines. So there's only countably many programs. So
Yeah.
there's only countably many numbers where there is a program to approximate it. So there's like a lot of irrationals out there where there exists no program to approximate it.
Yeah. Yeah, a lot by infinitely many.
Exactly.
Yeah.
So in some sense, if you pick a general irrational, there will be no way like for a computer to approximate it. Some irrationals, it might be different, like pi or square root of 2, because square root of 2 is like, it's a so-called algebraic number. It's the root of a polynomial with integer coefficients. So there it's like actually quite straightforward. Or pi of like these infinite series.
Yeah.
So yeah, for example, like pick your favorite like infinite series expression for pi and just cut off the infinite series, or like 1 over pi, whatever, and cut off the infinite series like at some finite term. That will give you a rational approximation of 1 over pi.
Yeah. I see.
But like for general irrational, there isn't a. I mean, it's a nice. Well, I don't know, nice, but it's something to realize that you cannot expect for a general irrational for there to be such a procedure, like a decision procedure.
And if I'm writing a proof, would I just say like we can pick rational numbers like approximating the decimal expansion?
Yeah, I think that works. Yeah, so and now we've like even shown something really strong, right? We have shown it for every single thing, for every single irrational outside this interval. Inside this interval, every irrational inside this interval. We've shown that it's actually a limit point of our set, but it's not in the set itself.
Right. Yeah. Yeah. That's true.
Yeah, that's really nice. And even like to tie back to our previous proof of it being closed, the idea was given any irrational, aka something outside the set, can we find a decimal approximation, like, or sorry, not decimal, rational approximation? And this is the same as given any epsilon ball around this irrational, can you find a rational number inside this epsilon ball?
Right.
Which was this was literally our proof, like our previous proof with like the complement is not open.
Yes. Yeah. Yeah.
So you kind of see how these two things translate to each other, like two sides of the same coin.
Yeah. Oh my god.
Yeah, all right.
Yeah, that's crazy. That's what... Yeah.
Yeah.
Wow.
Very nice. Very, very nice. And now, if you want, we can do the third one. We're going to show that it's not compact.
Sure, yeah. And compactness is this is the finite subcover definition.
Oh yeah, I'm definitely thinking of every cover having a finite subcover.
Okay.
So if we want to show it's not closed, it's because it's bounded, it's equivalent to show that it's non-compact. And to show that it's non-compact, we have to exhibit some open cover of our set, which has no finite subcover.
So we want now what exactly will that be? Let's see. An open cover with no finite subcover. It's got to kind of rely on infinite.
Yeah, it will not rely that much on this whole rational versus irrational. It's kind of well, let me see. Can we find an easy cover?
An easy infinite cover.
Yeah. Okay, I can think of it. Yeah.
Need a function that tells you if a rational is bigger or smaller than a number.
Why would we need that?
That's just what this Anuarak guy said. Anuarak.
Yeah. But there's some technicalities why a computer program can't do it for a general irrational, right? Because you can't necessarily decide if an irrational is less than or greater than a rational, because irrationals, finite space and stuff like that, finite time.
Yeah.
Yeah. So we have to come up with some open cover. So what if we do wait, let me see.
Yeah, an open cover doesn't jump out at me. But I feel like I have the least familiarity with that definition of compact.
Yeah, fair enough. This one's also not the easiest one compared to the other two. We're relatively straightforward, but I mean, okay, so suppose we have some cover, and so let's make sure that 0 and 1, the two endpoints, are included. So we have some small neighborhood around 0, some small open interval around 1. These are two elements of our cover, this
Sure.
interval. And then I want to make smaller and smaller intervals around different points. So for example, I make sure that let's see, around 0.1, I choose an interval of length 0.1, right? So this covers everything from 0 to 0.2.
Yeah.
Then but not including 0.2. Then 0.2, I choose an interval of length 0.05 open interval. And I keep
Yeah.
doing this. And this way I will make a cover of the whole interval. And yeah, it will just simply cover the whole interval.
Yeah. But we
Mm.
need the fact that if it's finite, it's not. Or there is no finite subcover of that. Does that hold true for that cover? If we remove
Wait,
any of
I'm
the elements.
thinking. I'm actually, because like thinking it from a meta point of view, right? If we
Yeah.
had, yeah, maybe this is harder because like the interval itself, like 0.1 with the endpoints, like, and we have all the numbers in between, we
Yeah.
know that that is compact, right? It's a closed interval. It's closed and bounded.
Yeah.
So there, every finite cover of that will have, let's see, we'll have a finite subcover.
Right.
So we need to cook up some cover of our set E, which is not a cover of the whole interval.
Yeah. Right.
Maybe this is more hard than I anticipated.
I mean, we can always come back to it too. It's not essential to
Yeah,
know that. That's just for
yeah.
fun.
I think we can come back to this one. I will keep thinking about it in the back of my mind.
All right, cool. Uh, this this is interesting. So like when they say this is like closure and interior, do they mean like in reference to the real numbers?
Yeah, that's a very valid question. I think so. If they provide no further context, um,
Yeah.
yeah, we would have to assume so. I mean, they should say that, I guess. But yeah, I would assume.
Okay, and basically, if we're closing under the real numbers, wouldn't this be just like equal to the whole interval?
Exactly. And why would that be the case?
I mean, it's just like all the throwing in also all the irrational numbers, which just completes.
Exactly. You kind of throw in all the limit points of the set. I don't know if you've seen this as a theorem or something, but that's what, or as a definition, maybe even. I don't know what your definition was, but that's basically what you do when you construct the closure. You just throw in all limit points.
Right. And would the interior be something like this? So it would be like 0 and 1. Well, the interior is just all the limit points union with like all the irrationals within that range.
Well, that's not entirely the case. Can you think of like why that's not true? Like what was the interior again, or what was your definition of it?
It's the I guess the points that aren't limit points. What is
No, not entirely, because every point in the set is kind of a limit point, because like the constant sequence converging to it. So that's not really
right? Yeah, that's a good point. Yeah.
So, I mean, I think this was a theorem we proved for one of your homeworks. It's like the interior is the largest open set contained in that set.
Oh,
But
yes.
I think
The
your
largest.
definition was something different. Oh, that exercise 4 for 11, that's some good shit. That's where topology starts.
Yeah, interior is just the largest open set.
Yeah.
So
Yeah, exactly. So they're around those points around where there does exist an epsilon neighborhood. So what should this be in this case? Like thinking back to our argument about why E is not open, right? We picked an arbitrary element of E.
mhm.
Like we showed it for an arbitrary element, right?
Yeah.
And we showed that there was always some irrational around every epsilon neighborhood of a rational.
Right.
So now this exact same argument tells us that around any point, like there is no epsilon neighborhood contained in the set.
So is then the largest set just the empty set?
Exactly. Like, yeah, the interior is empty.
Gotcha. So the interior can be okay. Yeah, that's good to know.
Yeah.
Yeah. Sweet.
Also for this compactness, yeah, I think. Oh, he's back. Wait, sorry, Vladimir is back.
Put a necktie. I don't have a necktie. You can send me one though. I'll drop my address in chat.
Give the people what they want. I think for this compactness thing, yeah, you have to do something more subtle, where it's like, consider some fixed irrational number between 0 and 1.
Yeah.
And we're gonna build like a cover where we pick maybe like any like some around any rational number in that interval. We're gonna pick some neighborhood centered at that rational number,
Yeah.
which doesn't include our fixed irrational number.
Yeah.
So this cover will always avoid that irrational number, and then you kind of can construct it, which I think is still not obvious, but you can do it, such that this cover that you've now made is actually doesn't have a finite subcover.
Yeah. Okay, I believe that. I think I hope there'll be like another cover problem in this actually, because
Yeah, maybe.
I mean, honestly,
damn.
like realistically, this is more
Not
what
even
the
going
exam
straight.
looks like. I think I'm pretty not in a bad spot.
Yeah, no, I think, I mean, you're definitely learning. I noticed that going quite well. But it's nice that they do many like topological flavored problems.
Hey, thanks for the €50. I guess I have to spend it on a necktie.
Damn, yeah. Oh no.
Although also like I had like not enough. I moved my money to like the wrong account, so my rent bounced, and I got like a $50 fine. So like that would also cover that.
Oh yeah, that's crazy. Yeah, fair enough. It's karma. The universe balancing itself out.
But
Crazy. So I guess Vladimir should donate another 50 for the necktie.
I mean, it depends on how nice of a necktie he wants me to get. Okay, what about 16?
I think this one we all covered, no?
K is bounded.
Here, okay.
K is closed. I mean, this one seems pretty obvious. Like, well, so clearly it's bounded. It's also
Yeah.
pretty clearly closed.
I guess
I'm just
closed, if you really follow the definitions, you have to show a little bit for closed, but it's not that bad.
I do think like that would be probably. Yeah.
Oh, 20s, that sounds very topological. Oh no, sorry, from 17.
Prove that any closed subset of a compact set in Rn is compact. Yeah, that is a good one. I'm not sober, so let's stay safe. What does that mean?
Vladimir has crazy plans.
Man, sometimes I just think about like what I'll be thinking about like 10 years from now or something. Like my college experience is like so weird for the average person's college experience. Like I was spending all day like talking to European grad students and like having money thrown at me by an oligarch. What a good life.
I guess good stories, right?
Yeah.
And on the other hand, otherwise we'd probably just be spending this alone doing real classes, which would be really sad.
That's how most people have to get through it. They can't.
Yeah, it's kind of crazy. Yeah, it's too bad you don't have like, because you said right, you don't really have like these exercise classes where you can just work together with people on problems. That's so useful, I tell you. That's like, yeah, it's how I got through real analysis in all my courses. I mean, for me it was like COVID times when I did real analysis, but it was still like we had the exercise classes online, and we had like a hand in every week that we could like hand it in together, like with in a pair. So it was just me and this other guy, like online on Zoom for like 7 hours a day, barely talking, just locked in astronomically. It was crazy.
Yeah, there comes a point in everyone's life where you just have to start locking in very seriously.
Yeah, although at some point, yeah, this was like real. When was this? Like beginning of 2021. It was like peak lockdown. It was not fun at a certain point.
I mean, yeah. Sorry, I just got thinking about this problem all of a sudden. If we're proving that any closed subset of a compact set is compact, I mean, we know that by Hein-Borel that it's closed and bounded. Like, well, we know that it's the subset of a closed and bounded thing, and we already know that it's closed. Can't we say that it's bounded by being the subset of a bounded thing?
Yes. So I guess the only like almost non-obvious. Oh no, in this case, I guess it's obvious, right, that it's closed. Yeah, so in this case, Hein-Borel kind of kills it.
Yeah.
There is again something topological going on in the background, I guess. Where you have for, I think you leave like, yeah, I think this should work for any topological space. If you have a closed subspace of a compact subspace, it's compact. Because let's see, like suppose if we think about open covers, like true topologists, suppose we have some open cover of this smaller space. I guess we can always extend it to a cover of the bigger space by like adding neighborhoods around each point, and then we can take like a finite subcover of that because the bigger space is compact.
Yeah.
I think something like this. But yeah, this is a fact which is true in any topological space.
And
But yeah, what you said with finable REL is perfectly good. I mean, they give you the theorem, so you use the theorem. Yeah.
that just seems like dead simple. I mean,
Yeah.
our subset is closed by assumption and bounded since it's the subset of a bounded set.
Yeah, I guess that's all there is to it.
Simple.
Oh damn, you read ancient Greek? That's goated. That's a true employability type shit.
Yeah, it's I don't know. The thing is with like reading ancient Greek, I would say is like, yeah, I technically read ancient Greek, like I've taken classes on it, but the step from reading like certain things to certain other things, like if you want to read really cool ancient Greek stuff, like original philosophy, that's like a massive difficulty leap because you just have to have such a big vocabulary and stuff.
Yeah, it's all that grammar. I mean, I had to do a little bit, like in the high school system in my country, like if you do a certain kind of high school, you have to do either ancient Greek or Latin.
Yeah,
I
did
chose
that
Latin
too.
because I fucking hated Greek. So I dropped ancient Greek like as soon as possible.
Yeah.
But yeah, it's tough out there. Like yeah, actually reading the original text I still have nightmares about it.
Yeah, I also had to do Latin in high school. It's very in some sense I kind of liked it over spoken language because it's like very algorithmic and like predictable.
That's true.
But it's also just it's just so much like busy work.
Yeah, that's true. And I never like really put the time into it, so I never got the algorithm down. So this was kind of that made it kind of hard, I think.
Yeah, if you could like really breeze through it, I think that would become very fun, but it requires a big investment.
Yeah.
Yeah.
Yeah, at some point, yeah, we didn't do too much, but we did read like the Seneca and or Epicurus, or like talking about Epicurus and like philosophy. This was like torture. That was crazy.
Yeah. Yeah. It is. I kind of wish I was better at those languages though, because like my dad, that's what his PhD is in, and like every word basically, he's like, oh yeah, that came from this and this, and it originally meant this, and like you just have such a cool perspective of the world. You know, like how the meanings of things have evolved over time. I would love to have that vision.
That's very cool. Yeah, that's very cool. If you're like someone who like actually really knows their stuff.
Yeah. Oh, what about this? This is another compact problem.
Let's see. I don't see it yet.
Probably
but the stream will be there in a second. A collection of compact subsets. Yeah, but it won't be super hard. But yeah, it's kind of related to a problem we had before.
Be a collection of compact subsets of Rn. Prove that the intersection of them is compact. Okay. And it's compact if every cover has a finite subcover.
Yeah. Although in this case, I think it might be useful. Or let's start with doing the Heine-Borel kind of thing.
Prove that. You mean closedness and boundedness?
Yeah.
Yeah, I guess. I mean, so if each of those sets is closed and bounded, their intersection is going to be closed. We've proved that before, I feel like.
I mean, technically we haven't, because this might be an infinite intersection, right? It might be
True.
So we haven't really done that. But yeah, it's a theorem again, or in general topological spaces, that arbitrary intersection of closed sets are again closed.
Yeah. So we have. All right, so the intersection of these guys, we want to show that the intersection of closed sets is closed.
Yeah, because the boundedness, I think this is relatively straightforward, right? Why this intersection of bounded sets should be bounded?
Yeah, I mean, because couldn't we take... It's just going to be whatever the smallest set's bounds are?
Yeah, so to show boundedness, we can consider any one of them and take those bounds. And that will also be bounds for the intersection purely because it's a subset.
Right, yeah. The intersection... Okay, but showing that arbitrary closed intersection is closed, so it contains all its limit points.
Yeah. I think this is also not too bad if you just think about convergence sequence.
Every convergent sequence within one of these converges
So
to
suppose
something.
you have some sequence which lives inside this intersection every term.
Yeah.
And it converges to something in Rn. And we want to show that something it converges to actually lies also in the intersection.
And yeah. Okay.
So yeah, it's kind of very straightforward. So because like the sequence lives inside the intersection, it also lives in every single one of the closed sets, right?
Oh yeah.
Every term.
I was thinking about proving it kind of like starting from each instead of starting from the intersection, but that makes it a lot easier.
Yeah. So, because what we kind of have to be clear on, like, what do we need to show, right? We're given an arbitrary sequence inside the intersection, and we're given that it converges to something. And now we need to argue that something lies in the intersection, i.e., that it lies in every single one of the sets.
Right, and it does because they're all closed, and anything in one of them.
Exactly, because if you take any one of those sets, your sequence also lies in that set, because it lies in the intersection. And therefore, because that set is closed, the limit also lies inside the set.
Yeah.
And so therefore it lies in every one of the sets, and therefore in the intersection. Yeah, that's just it.
Okay. What about give an example of an arbitrary union of compact sets? Need not be compact.
Yeah, this shouldn't be too hard. Just thinking of high-level again.
Arbitrary union of compact sets. Yeah, if they're bounded and closed, they need not be bounded and closed. I mean, could you just have a union that like goes to infinity and then it's not bounded?
Yeah, exactly. So what would be like a easy example?
I don't know, like 2 to n or something, and n is just goes forever.
Exactly, and you take like the closed intervals at every step.
Yeah.
Yeah, that works. Yeah.
You could also, I guess, do it so that it's not closed. Give it an arbitrary union of closed and bounded. I mean...
Yeah, you can, yeah. An arbitrary union of closed need not be closed. Although this is, I guess, slightly more awkward. But you can do like closed intervals where like maybe one endpoint moves, but it approaches some limiting value. So if you think about the closed interval like 1 over n comma 1,
Yeah.
the union will be like the half open interval 0 comma 1.
Right, yeah. I see. Which is not closed. Yeah.
Exactly.
Yeah. Yeah, that makes sense. But it is a little bit more awkward.
I mean, but your boundedness example was nice and simple, straightforward.
Yeah. Use this sequential characterization of compactness. I've never heard of that.
I think they mean like maybe your definition from Abbott. So what was it like? Every set is compact if every sequence inside the set has a subsequence which converges, and it converges to something inside the set.
Yeah. I know what you're talking about, yeah. I've seen that definition.
Yeah. I think, let's see, is this one gonna be annoying?
It's with Europeans because they're Europeans here.
It's true. Although, at this point, I guess the Americans should also be awake. I mean, you're the prime example.
Yeah.
US people work. That's true. US people always be working.
Not the unemployed.
That's true. That's true. I mean, yeah, college, whatever. Doesn't count.
Yeah, it's not really employment, I guess.
Yeah, someone
Sequential.
said Alexander got a job.
What did he get a
That's very
job
nice,
doing?
right? Yeah, that's also what I want to know. Also, I want to know how they know that Alexander got a job. They know each other.
Yeah. They can't just be telling stuff without telling us.
Yeah.
Apparently there's a paper called Claude Cycles.
Yeah, I just someone mentioned by Donald Knuth. It has to be good.
Learned yesterday that an open problem I've been working on for several weeks had just been solved by Claude 4.6 Opus. He's a mathematician, right? Or I guess computer
Sorry, who?
scientist. Donald Knuth.
Donald Knuth, yeah, he's a computer scientist. He's like quite famous. Well, he's somewhere in between, but he's like theoretical computer science. I think
Yeah.
he also did I'm not sure, maybe Chad will know. Like there's this famous guy who made like this famous algorithm for factoring prime numbers very fast on a quantum computer.
Yeah.
I think that's him.
Yeah. Oh, it's a joke. Because yesterday he was here all day.
I also didn't get it. I didn't get it at all.
Yeah. Yeah. He doesn't have a job. There's no way.
Probably. Probably, yeah. Probably refining his ethnic profiling skills via text.
True. He is really like, I don't know. And I haven't really heard someone disagree with his assessments.
That's true. Maybe people, maybe people are also just too afraid to dox themselves. But like, yeah, he's locked in. He knows what he's doing.
Yeah. Yeah.
Yeah, what about all the jobless US mathematicians? Yeah. What about them then? Welcome to the club. Well, I'm not from the US, I guess, but
Yeah, that's our government kind of sucks.
yeah. Also in my country, like they cut science funding like crazy. It's not fair. Like getting a PhD now is so impossible.
Wow.
Yeah, it's fucked up.
Why is that like? It's like against the interest of like the smart people of the world. It's really weird. It's like.
Yeah, it's kind of crazy. So I mean, of course, it's like all part of like this longer process, but we're at a government where they're very much anti the woke left, whatever that means, and to them that means like anyone in academia or on a university.
Yeah.
It's way too woke, so we shouldn't give funding to cancer or anything. No. Yeah. That's more or less how it went. Like, it's the TLDR.
I think the funny thing is though, like any country that does that is gonna eventually realize that the countries that aren't doing that are like gonna start doing way better economically.
Yeah, that's true. I mean, it's also not that bad because the government fell like within a year. They were shit, so now we have a new government who is, in some sense, a bit more reasonable. But yeah, it was some crazy like cuts to like especially then like all the smaller programs in universities, like a lot of the humanities,
Yeah.
the bachelors have simply ceased existing.
Yeah.
Or they were stopped like from 1 year to the other. It was crazy.
The case for us, yeah. Yeah. All right. Solving this using the every sequence has a convergent subsequence.
Yeah.
I mean,
Um, this one feels a bit awkward though. It's not a nice one.
Yeah. Yeah. I agree.
It's like, um,
Yeah. And I mean, actually, we've been doing a lot of compactness. Could we possibly do like a continuity question? I feel like the algebra and continuity is like always what messes with me.
yeah, that's true. Maybe let's do that. I also don't feel like this one. This one feels like awkward to do this way.
Yeah. How do I take care of my hair? Like, usually bleach. That's about it. Okay, so proving
Oof. Okay.
3x squared.
I'm also gonna whip out my tablet C. I'm not gonna do this in my head. All right. Wait. Wait, it's gonna be loud for a second. I'm sorry.
That's fine. All epsilon. No, it is a racism thing. It's not really about timing.
Okay, wait. Sorry, I had to go into my kitchen because I realized I didn't put my food in the fridge earlier, and
Oh, yeah.
the washing
Classic.
machine was going. Sorry, what were you saying?
Oh, nothing. I'm just trying to remember the definition with all the quantifiers of convergence.
Yes, yeah.
For all epsilon, we have a delta such that
I guess what's kind of interesting about the way the book does it, like the Abbott, and also
Yeah.
your course, is the order in which they introduce this. Like in a usual real analysis course, I would kind of expect this epsilon delta definition for functional limits. That comes kind of first, and then you kind of do these sequences. But I think it's very interesting how Abbott does it. Like by doing these sequences, I guess you put much more emphasis on like these topological aspects, which is really nice.
Yeah. It is nice. For all epsilon, we have delta such that man, I don't know. Like, the granular details of the definition of this are like it's loosely of this form, but that is not correct, I feel like.
For all epsilon, we have delta such that, I mean almost such that if x minus c is less than delta in absolute values, of course, then f of x minus c is less than epsilon.
So just
So it's like almost.
where the functions are swapped.
Yeah. So let me see. See, I think, or at least what I see on my screen, it should be flipped around. So you have if x minus c less than delta, then f of x minus f of c less than epsilon.
F of x minus c is less than delta. Wonder if I work well under pressure. Yeah, I might do that. Yo, check out my math streams. Okay,
Yeah, I mean, the evidence is out there. Sure.
Not the topological definition of continuity. That's what we used earlier to prove that problem, but avoid like all the work.
Yeah, wait, where did you use it?
Well, that's like we're using the epsilon delta definition, I guess.
Yeah. This is the topological space characterization of a continuous function, which very good. Very good.
Where is this damn functional limits, continuous functions? No, not the extreme value theorem. I guess I'm just looking for the simple definition. Composite continuous functions? No. Where are the continuous functions? Oh, there we go.
Yeah, there's characterizations of continuity, exactly. And they want like the first one, the epsilon.
Yes. For all epsilon greater than 0, there exists a delta such that, and x in A, of course, implies, yeah. Yeah. Okay. Alrighty. Let's say, okay, all right. Sometimes my brain just starts to zone out after too long. I heard recently, I wonder what your experience is with this. There's like only a certain amount of time in the day that humans can like be capable of hard thinking on things. It's like maybe 6 or 7 hours or something, and beyond that point you get kind of fried. And like you can push past it, but we're not really designed to do that.
I mean, I can I can believe that. I mean, I think there's probably like a lot of nuance to it. I don't really generally believe like when you have those kinds of statements like and they're presented like very black and white. But like I certainly think there's like some like we're not meant or not designed to like work all day. Also like especially doing like this with mathematics or like these really like intense things where you have to like have 100% of your focus like all the time, otherwise it's just useless. Like I noticed like also talking with other people, like I can't work like a full day 9 to 5, like actually like focusing it takes a lot of energy. You can only do it for like in like smaller.
And that's I feel like a lot of jobs, like knowledge work especially, like that expect you to work 9 to 5, like I don't know if almost anyone actually works like 8 hours concentrated at knowledge work. It's just like you get tired after absorbing a certain amount of.
No, I completely believe that. I think certain amount also exactly and certain time, like like at a certain point your brain just has to like recuperate. It's like I think in some sense kind of like sports for your brain, right? Where you just after some point, like you can work out more, but it's just bad for your body and you should let it rest.
Yeah. Yeah. All right. I guess, yeah, after this problem, let's call it then.
Yeah, maybe that's a good idea. Yeah, also this problem, yeah. Okay, I did a little scratch work and I think it's looks okay.
For all epsilon and delta. So the way to solve it is we're going to choose a delta and then get an epsilon in terms of that delta.
Other way around. We choose an arbitrary epsilon, and then we have to, based on that arbitrary epsilon, we have to choose a delta.
Gotcha. Okay. And like, what's the general strategy for picking that epsilon?
So we kind of, in some sense, work backwards. As in, we start with this f of x minus f of c.
Yeah.
We're gonna do some algebraic manipulation to it. So we can phrase it in terms of like this absolute value x minus c, which we can bound by delta. So in the end, we want something, I guess, which only depends on delta and c. So we get rid of the x dependence in some way. And from there, we can basically kind of read off what our epsilon should be.
Gotcha. Minus 5c squared. And then we got plus 2. Oh. Okay, and then this is all less than some epsilon. And, how are we going to get rid of the x's here?
So first, let's do some algebra simplification.
Like group similar terms?
Yeah, because in the end, we want to do something in terms of x minus c, because there we have this delta bound. So we will kind of want to express this kind of stuff in terms of x minus c things.
Plus 2 minus 2 will cancel out. So we'll get something like this. Oh, wait. That's c squared and that line is incorrect. But
yeah, x minus c, right? Yeah. That looks very good. So you can factor this difference of squares, right? As x minus c, x plus c.
Sure, yeah. Oh, yeah.
So then, yeah, this x plus c on the right should be x minus c.
Should it be? Oh, yeah.
So then we can simply factor out an x minus c.
Right.
Out of this whole expression.
And then we get 3x plus c minus 5. And, oh, okay, I'm starting to see the vision now. Okay. And then, like,
yeah,
you get a 3x plus 3c minus 5. And if we could move this to the other side and then try to get rid of x somehow.
I mean, yeah, this x minus c, we know that this is in absolute values. This is bounded by delta.
Yeah.
Yeah, and of course implicitly we're using things like the absolute value of a product is the product of the absolute values.
Right.
So we can split off this x minus c just with absolute values. And just say, so this whole expression that we have is less than delta times, what is it? 3x plus c minus 5. And so we just have to get rid of that x dependency in x plus c.
Right. And we can...
So yeah, let's...
What do we know about it? No, nothing. Go on.
So for this... So the next step, I guess, is to find an upper bound for x plus c, or absolute value of x plus c, rather. Or how I did this is, because we're allowed to choose our delta, right? We're allowed to choose our delta. We're going to choose it in something in terms of epsilon.
Yeah.
But for example, I can also make sure that I choose it like the minimum of something with epsilon and 1. So just to ensure that the absolute value of x minus c is less than 1.
Is less than 1, right, minimum. And then it's going to be something in terms of epsilon, but we don't exactly know yet.
Yeah, we don't know yet, but just so we make sure that the absolute value of x minus c is less than 1. And then what I did is, what it just comes down to is a little triangle inequality tricks. If I have the absolute value of x plus c, I can see this as absolute value of x minus c plus 2c. And on that, I can use the triangle inequality.
That's clever, yes.
Yeah, this is a useful trick where in these epsilon delta proofs, right, you're always going to have something like, I want x minus c, but maybe I have some other weird term in terms of x, like x plus c.
Yeah.
And then just, I want to get rid of this x dependence. So by having, we will see that making sure that x minus c is less than 1 will give us some bound on x plus c, which will be really useful.
Yeah. Wait, are you talking about splitting it within there or splitting it within the other?
Splitting it within the other. So this, I think of this kind of as like scratch work on the side of what we're doing. I'm considering just x plus c in absolute values on its own.
Gotcha.
And I want to first find a bound of this, and then we'll use that later.
Yeah. Which you can consider as x plus 2c minus c.
Yeah, x plus c you can see as x minus c plus 2c. And then you can use your triangle inequality to say that it's less than or equal to the absolute value of x minus c plus the absolute value of 2c.
And
at that point, I can use that this absolute value of x minus c is at most 1.
X minus c is at most 1. To bound x plus c, you mean?
Wait, let me see. Yeah, what you've written down now exactly. And at this point, we're going to use our assumption that delta is less than or equal to 1. So we know that absolute value of x minus c plus absolute value 2c is less than or equal to 1 plus absolute value 2c.
Oh, yeah. Gotcha. So we sub in 1 here.
Exactly. Yeah, this is the point where we use 1. So that got rid of the x dependence, right? That's the nice thing.
I see. That's a clever idea.
Yeah, that's a useful trick. Like, we have this x plus c, and we just want to express it somehow in terms of x minus c. And this is like one useful trick how to do it.
Right. I actually kind of like having this like that. Because then we've got 3 times 1 plus 2c.
Exactly. 3 times 1 plus 2c minus 5. Of course, you have to be a little bit careful with the absolute values. But we can, again, use a triangle inequality here to get some bounds on this term.
On the 1 plus 2c term? Or the minus...
Yeah, just hold the 3 times x plus c minus 5 in absolute values.
Yeah.
That one we want to get a bound for, and then we can use our previous bound.
Yeah, and we get a bound for it how?
So we consider 3 times x plus c minus 5 in absolute values. We can, again, use a triangle inequality to put that this is less than or equal to absolute value of 3 times x plus c plus, well, absolute value of 5, or absolute value of minus 5, I guess, which is just 5.
Yeah.
And then we can factor a 3 out, so we get 3 times absolute value of x plus c plus 5. And now we have a bound for the absolute value of x plus c. So we get that this whole term is bounded by 3 times 1 plus 2 absolute value c plus 5. Yeah, it's a bit hard to say.
Yeah, I see what you're... Like that. Wait, no, we're splitting...
Yeah, no, I guess that's true. You just want an absolute value around the c inside. So 1 plus absolute value of 2c, or 2 times absolute value of c, same thing.
Right. Gotcha. We just have to be careful with that. And now that we've got this, we can just start moving things around to get our
absolute. Wait, 1 plus the absolute value. I guess that makes a difference. Technically.
1 plus the absolute value.
Yeah. So now you have like absolute value of 1 plus, and then you just remove the outermost absolute values.
Yeah, I see. And then our expression overall, or like our delta.
Wait. Now you have like double. Wait. But now you have wait. Now you're back to what you had before. Like you should remove the absolute values around 1 plus 2c, and instead put absolute values at just around 2c.
I see. We just need the parentheses there. I was kind of using them as parentheses.
Yeah, that's technically something different. You suffer a bunch for nothing. Okay, yeah, so what you have now is really nice. I just really don't like this epsilon minus 5 business. I really don't like that.
What's wrong with that?
It's gonna be a negative number in general if epsilon is small. So I really dislike my absolute value being smaller than a negative number.
And what is there to do about that, though?
It's just a small mistake in the algebra. So now we have x minus c times some constant in terms of c. Let's just give this thing on the right a name, this 3 times blah 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 plus 5.
Yeah.
right? Let's just call that. Yeah, I don't know. You come up with a name.
Oh, wait, it's 3 times that. The 5 is in there. That's, yeah, I see.
Yeah, the
I
5
see.
is in the parentheses. Yeah.
Yeah. So,
Yeah, and exactly what's in there is not all that relevant. It's just a positive number. That's all we really care about.
yeah. Yeah, I see.
So now we should really use that our x minus c is less than delta. So we get that our original expression, this difference of this f of x minus f of c in absolute values, that this is strictly less than our delta times this constant, this positive thing, whatever it is. So then if we see that if we choose our delta to be epsilon divided by that constant,
Yeah.
then we're good.
There's a bunch of scratch work here, but well, you said choosing it as the minimum of 1 in that constant.
Exactly. Yeah. Exactly. The minimum and of 1 and epsilon divided by that constant. Yeah.
That
Very
constant,
much
I guess,
so.
is 3 plus. I mean, it's like 15 plus 2c if you simplify it. Or plus 6c. I mean, it doesn't.
Well, you have to be. The way you wrote it in your last line, this constant, there's again like a little bracket mistake, right? This 3 scopes over 1 plus 2c, but it doesn't scope over absolute value 5. But when you wrote epsilon divided by that, the 3 all of a sudden does scope over that.
You're right, yes. Yeah.
So yeah, you don't even have to simplify it. Like what I would do is simply give it a name like m, or I guess we already chose c or something like constant or y or whatever.
Yeah.
Just give that expression a name and just plug it in. It's really like not interesting like what exactly it is.
Yeah. Let's see. I don't want this equals. Yeah, call it m. Okay, and then from there, like, do we have to work backwards?
I mean, in this case, we don't really have to work backwards, but we do have to write it down a little bit differently. So we should be careful in writing this down. So we should start with like let epsilon greater than 0 be arbitrary, and then choose delta such that blah blah blah. Consider an x such that x minus c is delta and x not equal to c, blah blah blah.
Yeah.
We should first write all of this down carefully, so then we know like what is given and what assumptions we have. Then we can worry about like the algebraic manipulation.
Right. Okay. Choose. Let epsilon is arbitrary. Let Okay. And then this is almost done, but
Exactly. Yeah. And I guess you should then, once you write your proof, you should introduce your constant m before you say choose delta. Just you can literally like drop it out of thin air. You can say let m equal to this, whatever that thing was.
right. Yeah. Sweet. And is anything in this algebra incorrect?
No, the algebra looked pretty fine up until the last step, but we can. But we might write it down like slightly differently. So we start. So we want to show that this first expression is less than epsilon. So how will our algebra look like? We will start with that first expression, and then will come like a bunch of inequalities. And then at the very end, only the epsilon will pop up. So all these smaller than epsilons in these between steps, we don't need. And for now, as it is written now, it's also not entirely clear like that the bottom line is less than or equal than the top line or something like that.
Right.
So we should make, or like, where are they equal? Where are they strictly smaller? Where are they less than or equal? Like, this is what we should make clear. So it becomes like a long chain of equalities and inequalities.
True. And instead of epsilon, we're starting with delta.
No, we're just I guess after we choose delta, we should say let x be such that it's in the domain of the function. Well, that's just the real numbers, and the absolute value of x minus c is less than delta, and I guess strictly greater than 0. So x is not equal to c.
Yeah.
So I guess, that we should do first. Just saying that. After we've chosen our delta, of course. And then, after we've introduced x, then we literally just start with, we're just going to do one long algebra step, basically. We start with this expression we want to bound, which is literally just absolute value f of x minus absolute value f of c.
Yeah.
And then we're going to make like one long chain of inequalities until we get epsilon at the end.
Right, I see.
So we just start with like what's on your first line, basically. Before the less than epsilon, we're just going to delete all those less than epsilons. We're just going to start with that algebraic thing. And then we're going to like connect all those different lines, which are now beneath each other.
Well, yeah. Well, that's equal. That's equal to the line below. This is kind of a weird way to do this, but that's equal.
Let's see. Yeah, the first step is just equal. The second step is equal. The third step is equal. And then in the fourth step, I guess that's So at that point, I guess, maybe you can also put this scratch work of how to get this inequality for 3x plus c minus 5. Either you put it in at this point, like you break your chain of inequalities and you get some new text where you say, notice that blah, 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 and then you can continue, or you do it already at the very beginning, where before you start your... so after you've introduced your x, you can already say, like, note that you kind of, again, drop it out of thin air, like, note that 3 times x plus c minus 5 in absolute value is bounded by our m. And I guess you should put like the in-between steps from how to see that.
Put 1 plus absolute value to c since, oops.
What's going on there?
What's going on where?
X C plus C plus 5.
At what point? At what line?
Yeah, no. Now it's better.
Times 2c and x minus c is bounded by 1.
Yeah.
Where'd we get the plus 1 in there again?
So we have like x absolute value x minus c plus absolute value of 2c, and we just use that absolute
plus.
value of x minus c. Yeah, plus. And then we use that
was-
absolute value of x minus c is just less than or equal to, or strictly less than 1, I guess.
Yeah. Yeah, and we can say it's strictly less than 1 because we can just say it's arbitrarily close.
Yeah, just by our assumption on delta.
Right, yeah, that's the min. That's such a clever trick.
Yeah, that's a really useful one, that this minimum basically allows you to have multiple inequalities be true at once for delta, basically
Yeah.
as many as you want. That's how to think about it. Like, it's like, what would I really like? It's like, I will want my delta to be less than this epsilon over m, but at the same time, I would really like it to be, less than 1 or something else. And in this way, I can just force this.
Yeah.
And again, note that this 1 on itself is not like that interesting, right? I could have picked any positive number. I just picked 1 because it's easy.
Right.
So we have this bound for x plus c, absolute value of x plus c. From that, we should derive the bound that absolute value of 3 times x plus c minus 5 is less than m.
Is less than m. I mean, but isn't that algebra like kind of self-explanatory by the work down here?
Yeah.
It's like it's.
I mean, but now you kind of, in your end proof, you will not have the work done anymore except at this point. So in the end proof, it should be somewhere, and this is the right point. That's kind of the.
I guess you're right. Yeah.
Because we will clean up the scratch work towards the end, so you will not see that algebra again there. So I guess it should be mentioned here.
Which would just be saying like, we're simply making this substitution.
Wait, let me see until it updates.
Or do we just show plugging in this value for?
Yeah, you can just say now. Let's see.
M instead of N notation.
Yeah, to be really complete, I would start with because that's kind of what you want to show. You want that. What you want at the beginning is this 3 times x plus c minus 5 in absolute values.
Oh.
And then the first step is to say I use my bound that I just had to get 3 times 1 plus yada yada, and then I have to use the triangle inequality once more or something.
Right.
Yeah, this is kind of how real analysis proofs be. It's kind of nasty.
Yeah, 3. And the triangle inequality is just happening with the 5.
What do you mean?
That's we're just separating out the 5 here into its own.
Yeah, although we start with the way you've written it now on my screen, like the absolute values should go around the whole expression. So you should have 3 times x plus c minus 5, like the whole thing in absolute values.
Right.
And yeah, around the x plus c, it's just normal parentheses. Yeah, exactly. So then, yeah, you get out the plus 5 with the triangle inequality. I guess you don't necessarily want an implication arrow between these. You want like a less than or equal.
Right.
Or I guess it's strictly less than.
Yes. Yeah. By the triangle inequality, and then.
By the triangle inequality and our previous step.
And then that equals m.
Exactly, and that's just m. So now, yeah, the point of all of this was to get like that the very left side is less than m.
Yeah. And then plugging in m at the end there, we should be good.
So exactly. So now we're at this point in our derivation, which is like in your code. Oh, I don't know which line. I think like 295 or something.
Yeah.
Or 294, where it's like, yeah, 294. Where you have like this x absolute value x minus c times absolute value of 3 times x plus c minus 5.
Yeah.
And now you literally substitute in that we know that this second thing is less than or equal to m. So we get absolute value of x minus c times m. Yeah, less than or equal to that. Also, I guess one little thing, with your just like the way things are ordered now, your assumption like that the absolute value of x minus c is between 0 and delta, this should be put earlier. Like you have after let x be in the domain and then it should come there. So before this bound on our absolute value of x plus c.
Before our bound. Before our bound of x plus c. What line number are you talking about? Like up here, it's an x.
So I want the basically at the end of 282 should that's where this, yeah, you kind of just broke it up. You have this like 282 ends in and let.
Yeah.
And towards the end of that line, it should say 0 less than absolute value x minus c less than delta.
For the bounds of x.
Yeah, so like we first properly introduce x.
Oh, I see what you're saying.
We also need to say that
I see.
to have x minus c less than delta, because in our derivation afterwards for this absolute value x plus c, we use that absolute value of x minus c is less than 1. Because we know it's less than delta. So
Right.
we really have to do this beforehand.
I see what you're saying, yeah. And then, I mean, we don't, I already made the substitution, this is fine.
Okay, exactly. So now we're looking very good. So now we have x minus c less than or equal, x minus c in absolute value times m.
Yeah.
And now we want to use that absolute value of x minus c is just strictly less than delta. So we get that absolute value of x minus c times m is strictly less than delta times m. And this we know is just equal to epsilon, or less than or equal to epsilon.
Right, because we're going for the epsilon, totally.
Exactly. At the end, we just want epsilon to pop out.
Yeah. Well, okay, wait. Delta epsilon over m. So it would be delta times m. Yeah, I see. There we go. Yeah.
Let's see.
Well, that extra m, I'm a little confused on.
Yeah, I don't know, or maybe it takes a little bit for the stream to update, but now it's written down a bit weirdly. So I'm happy up until say line 294.
Yeah.
Like where we have absolute value of x minus c times m.
Yeah.
And just after that, the next step is to simply use that absolute value of x minus c is strictly less than delta. So the end of 294 will be like a strict inequality instead of a less than or equal. And then on 295, it should say delta times m, nothing more.
Is simply, oh yes. Simply less than delta m. Yeah, the way these things are chained is interesting. And that's less than...
You have to be careful about it.
Which is less than epsilon.
Yeah, less than or equal. Well, we have delta now, this minimum, right? So delta is, we just know that's less than or equal to epsilon over m.
Yeah. Okay.
So let's see.
Yeah.
Okay.
And then...
Yeah, I think...
Do we just have to invoke?
The way it is now, I'm very happy. Like, this is the total thing. And, like, the one thing to note here in this long chain is that, I mean, we've used, like, equalities and inequalities, but the thing to note is that there was at least one point where strict inequality showed up. Therefore, we may conclude that the very left side is strictly less than the very right side. I guess this is like a detail which is kind of necessary here.
Right.
So now we have exactly what we want. We have that the very left side is strictly less than epsilon, which is what we needed to show. Yeah.
Damn. Oh, that was some really good, rigorously correct algebra steps. That was good.
Yeah. It's like you really have to be a bit careful about these absolute values to get everything right. Then maybe one thing to ask or note, like for the sake of generalization, right?
Yeah.
Do you see how one would? Because we've now done for quadratic polynomial.
Yeah.
Do you think you would be able to do this now for any quadratic polynomial? Or maybe even for any polynomial at all?
I mean, quadratic polynomial seems pretty obvious because, like, the constants are just going to be kind of shifted around and you're going to be able to factor out the x minus c. Any polynomial at all, you would probably just use, like, the binomial theorem to factor out what you need.
Exactly. Perfect. Yeah, you're going to factor out this x minus c everywhere because you're going to get like lots of terms like x to the n minus c to the n.
Yeah.
And then you're going to factor with your binomial trick like this x minus c, like to the very outside. Yeah. And then you're going to get things like x plus c, like we got for the linear term or for the quadratic term here. Or then for the higher ones, you're going to get like other sums of x and c. Yeah. And then you're just going to basically keep repeating this triangle inequality trick and the fact that you may choose delta less than or equal to 1 to simply get bounds on all those terms.
Right, yeah. Yeah.
And this will work. You just keep applying your triangle inequality, and it will be probably some insanely huge number. But this is completely irrelevant, because we're just gonna call it m at the end, and we're gonna say delta is epsilon over m.
Yeah, right. And that is cool. And then you can see like, oh, my ski pole fell. You can see that everything is like every polynomial rigorously is continuous, which makes sense.
Exactly. That's like one way to prove it.
Yeah.
It's very nice. I mean, the
Yeah.
other way would be to, yeah, you can in general show that if you have two continuous functions, then
Yeah.
their product is also continuous and their sum. And like you can build a polynomial of sums out of sums and products of like the identity function and like constant functions.
Yeah.
But this is like a very direct way to do it, and it's fairly feasible. Like for any polynomial, you can just write this down.
Right. Yeah.
Yeah, Vladimir getting called out as he should be.
Yeah. I mean, cool. I guess like I think my brain is pretty fried in terms of like what I've done today, but honestly, like I feel pretty solid about this exam.
Yeah, nice. Yeah, I understand. My brain is also fried. When what time do you have your exam tomorrow?
It's at like 3 in the afternoon, so I could study a bit before it for sure.
Yeah, you have to see, I guess. I don't know, it depends kind of from person to person, like if that works for you or not.
Yeah, I think. Yeah, I'm not sure honestly. I guess I'll try it.
Yeah, but yeah, you definitely shouldn't do too much and take like a proper break before the exam. I don't know how long it is, but that's always important for me to
Yeah.
really like force yourself to have a break and to not think about it like beforehand, so you can kind of recuperate.
Yeah. All right, I'll